Okay, welcome to the course participants in the second lecture of the 95th outreach program. So yesterday we have discussed the basics of the global navigation satellite system and the four primary systems, that is the Navistar GPS, GLONASS, Galileo and BEDO. And then we have discussed about the functioning of that, how we do the survey, the static surveys, rapid static survey, stop and go survey and the kinematic survey. So these we have discussed along with the differential GPS technique. Today our topic is on the satellite based augmentation system and the Indian Regional Navigation Satellite System, that is IRNSS. So first we will take up the IRNSS and thereafter we will continue with the SBAS system, because IRNSS is also part of the overall GNSS system and it is a regional navigation system. So SBAS we will take up at the last. So the Indian Regional Navigation Satellite System, as we all know that the Honorable Prime Minister has named it as NavIC also. So the common name which is used for IRNSS is now the NavIC, which means navigation with the Indian constellation. This provides us the PNT services, that is the position, navigation and timing services all over the Indian region and up to 1500 kilometers beyond its boundary. So that means the services are available to the neighboring countries also. If they want to have the IRNSS services, they can also use it. So in similar to the other GNSS systems, this also provides the latitude, longitude and elevation above the WG64 datum, along with the navigation facility and the time. Two types of services are provided by IRNSS, that is the standard positioning service and the restricted service. That is again in line with the other systems which have been developed and yesterday we have discussed. The accuracy which we are getting from the IRNSS is of the order of 20 meters. So it's a very conservative measure actually, so that the users have a safe side, and otherwise what we have found that the accuracies are much better than 10 meter also when we are doing the observations through the IRNSS receiver. So the objectives of the IRNSS are in line with the GNSS systems again, provide the PNT services, and it has been designed in such a way that most of the constellation is seen by the users all the time, especially in the Indian region, and this is independent of other GNSS systems. So that is one thing that we should be proud of, that we have our own satellite-based navigation system for our regional requirements with a quite large footprint also. So primarily what we are using in it are the satellites which we have placed in the geostationary orbits. So 3 satellites we have put in the geostationary orbit and 4 satellites we have put in the geosynchronous orbit as shown in the figure. So these are the 3 slots at 34° easting, 83° easting and 132° easting, and 2 satellites are in the geosynchronous orbit. So that makes it a total of 7 satellites. So like that we are using the 24-hour orbits, we can say 3 in the equatorial plane and 4 in the inclined plane. Now this provides us a facility for utilization in the terrestrial, aerial or marine navigation environments, and the IRNSS services are useful for the disaster and fleet management services also. So the first satellite, that is IRNSS 1A, it was launched in the 2013 year, and between 2013 to 2016, in a short period of 4 years, we have launched 7 satellites. Thereafter, the 8th satellite, which is IRNSS 1I, that was launched on 12th April 2018. So currently we have launched 9 satellites as of total. So 1 satellite launch was not a success, and the remaining 8 satellites are in their designed orbits. So out of these 8 also, now the 7 satellites are functioning completely, whereas the IRNSS has 1A has a bit problem in the timing. So as our requirement is to have minimum 7 working satellites, our IRNSS is fully functional. Satellites have a designed life of about 10 years. So the elements, again, as we have discussed, the 3 basic segments of GNSS. So IRNSS also have 3 segments. That is the space segment, ground segment, and the user segment. So in the space segment, we have 3 satellites in the geostationary orbit and 4 satellites in the inclined geosynchronous orbit. So both these orbits, both these type of orbits, basically, they have time period of 24 hours. Now 2 orbits which have 2 satellites each, that is in the 2 inclined geosynchronous orbits, they intersect at equator at 55° longitude and 111° longitude. With the currently active constellation of 7 satellites operational, we have further plans to launch 4 more satellites, which will make a total of 11 satellites, in which 4 will be spares. And these 4, once they are operational, they will provide a better coverage and better accuracy, because redundant observations will help us in better computation of the coordinates. We can apply the least square adjustment techniques when we have redundant observations. So more than the minimum number of satellites required, which is 7, will help us in the acquisition of better data with more accurate coordinates. So as explained, the 7 satellites, 3 are in the geostationary orbit and 4 are in the inclined geosynchronous orbits. So IRNSS 1A carried 2 type of payload navigations, which are contributing to the navigation and the ranging payloads actually. So IRNSS 1A is having some issues with the timing equipment now, the clock. The payload is operating in the L5 band and the S band. A highly accurate rubidium clock has been put in the IRNSS satellites. And besides this, for the ranging purpose, the C-band transponder is used, along with another facility for laser ranging, that is the corner tube retroreflectors are also placed on the IRNSS satellites. So these are providing us the L-band signal at 1191 megahertz and 2491 megahertz. Here we can note that whereas most of the other satellites, they have been working in L1, L2 or L5 wavelengths, we are basically working in the L5 and the S band, because these are basically allotted by the International Telecommunication Union. So the international body has provided us with the L5 and S band. There is a possibility that in future we may get L1 also. So we are having the right-hand circular polarized signals, which we are using in it for the positioning. In this, we are using the solar panels, which generate a power of 1600 watts with a payload power requirement of 900 watts. So quite well-designed power requirements are there. And for other communications, C-band transponder is also available. So basically, our carrier waves are in the L5 and S band. That we have to understand. The signals and the satellite constellation is designed in such a way that we require the minimum constellation of satellites to provide a good geometry. Okay, so because we require a minimum of the DOP value, as we have discussed, 1 to 3 is considered very good, and then good, and then we have to up to 6 only we are considering DOP to be good for surveying. So that kind of constellation has been estimated and executed. Then optimal DOP, as we discussed, then the orbital slots also, as we have put all the satellites in the geostationary orbit and geosynchronous orbit. So these slots also we receive from the international body because these are very limited slots. So considering them, we have prepared a best optimized solution for the IRNSS. Then coming to the ground segment for various activities. So we have IRNSS navigation control facility, which includes IRNSS Navigation Center, IRNSS Network Time, then CDMA ranging stations are there, and laser ranging service is there for the retro reflectors. So currently in India, we do not have the laser ranging facility. It is under development in Tamil Nadu, but we can use the laser ranging services of the other countries. Then we have IRNSS range and integrity monitoring stations, and then IRNSS data communication network is there. So besides this, we have the IRNSS satellite control facility for the telemetry, telecommunication, and land uplink stations. And then we have the IRNSS satellite control center. So like that, in India, we have different ground segment facilities for better communication with the IRNSS satellites. At Dehradun also, we have a IRDCN for the data communication network and the IRIMS facility at IIRS Dehradun Center for communication with the IRNSS satellites. User segments. So all of us, we fall in the user segment, those who are using the IRNSS services. So we can get single frequency receivers, which get signal from either L5 band or either S band. Or we can have dual frequency L5 and S band IRNSS user receivers. Then we can have dual frequency L5 and S band receivers, which are working alone, or they can be combined with the other satellite navigation systems like the Navistar GPS, GLONASS, and Galileo. So these kind of receivers are currently available, and we can utilize this for the PNT services. This shows the schematic diagram for the various infrastructure on the ground and in the space for the IRNSS. So we have the spacecraft control center. We have as we have discussed in the previous slide. So we have all the centers for the purpose of the communication with the satellites and to do the ranging also, and the uplink stations also. As I have discussed yesterday, that from the single and dual frequency geodetic receivers, we have now come down to the Android-based smartphones. So there a lot of programming scope is there, and IRNSS signals are available. So based on that, different apps can be developed. So we have the version 1.1 and 1.2 also has been released now. So those signal in space interface control documents are available from the ISRO website. These can be utilized by the programmers for their app building. Some of the services are already operational, like the high wave, cyclone warning, tsunami, and no warning. So these services are available to the fishermen for their safety. Besides this, the IRNSS signals are also recognized by the International Maritime Organization now, which is part of the worldwide radio navigation system for the operation of IRNSS in the Indian Ocean region. So this range is from 5 degrees south to 50 degree north and 55 degree east to 110 degree east longitude. So now India is the fourth country after US, Russia and China to have a regional navigation system in the oceanic area, and which is certified by the IMO. So various applications are possible with the IRNSS, like for terrestrial, aerial and marine navigation, for disaster management, natural resource management, vehicle tracking and fleet management. So Accord System is one of the companies in India which is providing the IRNSS receiver. In the geodetic category, the Septentrio antennas, they also have capability of receiving the IRNSS receiver. The Leica and Trimble products are also receiving the IRNSS signal now. So it can be very well utilized in all over the Indian region and the neighboring region. So these signals and the applications can be integrated with the mobile phones also. IRNSS can provide the precise timing. It can provide the mapping, surveying and geodetic data capture capabilities. Terrestrial navigation is very much possible, and people are using it in the mobile. Various apps are there where we are getting the IRNSS signals also. Then scientific research is also going on in the atmospheric studies, crustal movements and the crustal deformation. So in this course, you are going to see the various experts in these domains also who are working in ISRO on the atmospheric sciences, applications of the GNSS and the crustal movements also. Then there are business solutions also which are possible using the GNSS in general or IRNSS services also in particular. Applications are there. So these are some of the IRNSS hardware which I am displaying here. So these are available from the Accord systems. IRNSS dongle is there, then IRNSS L5 antenna is there. Then in the smartphones, Qualcomm chipsets are coming like Snapdragon 720G, 662 and 460. So these are also providing very good accuracy. Mi8 actually, which is Android based smartphone, it has capability to receive dual frequency raw data, which can be programmed to provide its own solution independent of other systems at that point of time. So this is one development which took place in 2018 actually, and experiment has shown that it can provide an accuracy of the order of 1.5 meter. So single point positioning is possible by the use of the smartphones, or we can have the precise point positioning also. So this kind of solutions are now coming with the mobiles also. If your project requirements are met with this kind of accuracy, then at that time it is much more useful for you to handle this portable solution rather than going for a still high-end GNSS receivers. However, if you require further more accuracy, like in case of the crustal movement studies and many other studies where you require centimeter and millimeter type of accuracy, there we have to use the geodetic class antenna only. The IRNSS signals are fully approved by the global standards body 3GPP, and they are available for the mobile telephony, and they can be used in the 4G and 5G market also, and for the Internet of Things application, IoT applications also. So all these developments has already been taken place. Now it is more about making more and more use of the IRNSS signals for our applications, because it is our own regional system which is under full control of ours So we can be more dependent on this rather than any other solution. Then coming to the satellite-based augmentation system. So as we have discussed yesterday, that most of the receivers what we are utilizing in the standalone mode, they are capable of providing us 10 to 20 meter of standalone accuracy. Okay. To have a star point here, let us also note that the latest report says that if we are having the carefully fabricated GPS in the latest equipments, then it is possible to get 3 meter horizontal and 5 meter vertical accuracy also for 95% of the time. So these two things we have to understand clearly, the 10 to 20 meter thing and the 3 meter and 5 meter vertical and horizontal accuracies. Now these accuracies do not provide solutions for some of the real-time applications like for the aircrafts or the landing and takeoff or the en route operations. So in this case, what has been done that the ICAO has come in the front, which has the responsibility to develop the standards and procedures to support the communication, navigation, surveillance, and ATS systems, air traffic management systems, for the global movement of the aircrafts from one country to another country or within a country. So ICAO has also been an important party to the GNSS goals and definition. Yesterday we have seen the definition provided by ICAO also. So what has happened that for having a real-time higher accuracy, what we have done that we have established multiple ground stations all across the globe. So different agencies have developed for their own countries. And these ground stations, many of them are on the airports or near the airports also. Okay, because they are much more useful for providing high accuracy near the airports, which can assist in the takeoff and landing of the aircrafts. So at these ground stations, we know the corrected values. So it is one kind of application of DGPS only. So what happens when the aircrafts come in the vicinity of the airport for landing? So using the broadcast ephemeris data, which is coming in real time and from the known coordinates of the ground stations, the errors can be computed at that time and the correction parameters can be generated for the aircraft or any other user also for any other application per se, provided they have the SBUS enabled receiver. So this SBUS basically provides wide range or regional augmentation through the use of additional satellite broadcast messages. Now, what are these additional satellite broadcast messages? These are the correction parameters. Okay, and which are actually sent from the ground stations to the geostationary satellites, and the geostationary satellite in turn broadcast it back to the end users. And this all is happening in the real time. So that is why SBUS is very important for use in the real-time applications. It is also synonymous with the wide area differential GPS. This is the schematic diagram. So let me explain this to you. That we have reference stations established by different agencies, like in case of ISRO has established for Indian region in along with the participation of the Airport Authority of India. So we have established different reference stations. Now these are already surveyed stations with the corrected values, and from the broadcast ephemeris, which is coming from the GPS satellites, we are able to compute the errors and generate the correction parameters. So at the master station, and those correction parameters are uplinked to the geostationary satellite through the uplink station. So for our SBUS, which is called the Gagan, we use the INSET 8, GSET 8, GSET 10, and GSET 15. So 3 satellites we are using for the Indian SBUS. So we will come to the details of them further. And this all is done in a very trustworthy manner, maintaining the integrity as per the performance-based navigation manual. So in addition to the GPS satellites, what we are using are the geostationary satellites. So let us understand that when we are talking about the satellite-based augmentation system, they are not independent services. They are actually dependent services because the basic feed is coming from the GPS satellites only. Okay, in certain cases, like in case of European system, they use the GPS and GLONASS both. And in the higher version which they have planned, they will use the GPS, GLONASS, as well as the Galileo also, because Galileo has not completed fully. So like that, different designs are there. For Indian system, we are using the GPS. And these geostationary satellites are used as the repeater for the corrected messages. Okay, so that the correct parameters are sent to the users. So for different global regions, different services has been developed. Like for US, it is wide area augmentation system. For Canada, it is CVAS. For India, it is Gagan, that is GPS aided geo augmentation navigation. So as the name say, basically our system Gagan is dependent on the GPS feed. So in the input is from the GPS. So let us understand the difference here itself. See, when we talk about the IRNSS, it is totally independent system over which provide PNT services. But for the Gagan, we require the feed from the GPS satellites. Now, European geostationary navigation overlay system, that is IGNOS, is used for the Europe, and similar systems are working for the Japan, Russia, China, and the Caribbean countries. So they also have similar systems for their regions. Besides that, there are some other high accurate systems like the GDGPS, Global Differential GPS System, which is also called the National Level DGPS by the US. So then there is a course network all across the globe and the setup of IGS stations. So all these combined together actually provide us in a lot of solutions for various applications, ranging from navigation to the tectonic movement studies. Now, as we have seen in the yesterday's presentation that the four main systems, that is the GPS, GLONASS, Galileo, and BEDO, all of them work in different ellipsoid systems. But as I yesterday indicated, all the transformation parameters are known. So although the datums are different, all of them can be brought through mathematical computation into a one system. Now that is where we need the trust that after so much of computations, what we are getting, is it correct actually? So that integrity has to be maintained for the navigation system, and it is being maintained because all of the agencies are cooperating. And basically why this SBAS has come primarily across the globe. So basically to provide very high accuracy to the users and the aircraft industry. So earlier the aircraft industry was mainly dependent upon the VOR devices, which are very high frequency omnidirectional range devices, and the DME devices, distance measuring equipments. So that where are they? That is always known. Okay. So, and these systems were actually used all of the time, and especially during the World War, also some systems developed like the G and the Sony and the console systems combined with the services from the Omega, Chaka, and Lawrence also. So these systems has also been integrated and utilized for providing higher accuracy. However, because of the technology development, now we can fully depend upon the SPAS system. So that is what we are trying to understand, that SPAS provides us very reliable accuracy. And as of now, as of December 2021, US has about 1,209 airports which do not have instrument landing system. Okay. Otherwise, what is happening? That all the airports, they have ILS systems. So electronic landing is possible with the electronic systems available. So pilot will know the center line of the runway through the electronic devices. But in the case when some of the airports, they do not have such facilities, the landing can be directly done with the SBUS system. So, and it is operational at 1,200 airports across US, where the total number of airports are about 1979. So out of them, 1,200 are non-ILS airports. So they are extensively using the SBUS based landing, takeoff, and en route operations for the aircrafts in their country. Similar services we look forward for in India. Services are already operational, only the aircraft has to be equipped with the Gagan enabled receivers, and they will have large advantages. Now, when we are having a high frequency antenna at the airport, we can have a local area augmentation system also. So directly the antenna can send the corrected parameters to the aircraft, as well as it can send to the geostationary orbit, so that the geostationary orbit based satellites can further disseminate it to the users. So these are the footprints for the Gagan, combined footprint of the three geostationary satellite, GSAT 8, 10 and 15. So this is GSAT 8 and GSAT 10. Initially 15 was kept inactive, however it is also active now. 15 was kept as a spare. Similarly, other regions of the world. So these are basically the geostationary satellites. See now these VAS PRN 135. This is the PRN code for the geostationary satellite maintained by the US agency for the US region. Okay, then PRN 138, PRN 133. For the IGNOS, it is PRN 120, PRN 136, PRN 126. For SDCM, that is for the Russia. And then for the Chinese region, also there are similar system, and for the Japanese region, AMSAS is there. So AMSAS is using the MTSat satellites, which is there maintained by the Japan actually. So it has a PRN code 129. So similarly, we have the services from the geostationary satellite all over the globe. Now this is in addition to the GPS GLONASS satellites, okay? Because as I told you, IGNOS is using the GPS as well as the GLONASS signals. In India, in Gagan, we are using the GPS signals only. So what happens that with the help of the SBUS services, it becomes possible for us to fly point to point. Okay, we can have straighter paths. Currently, what happens when we fly from one place to another place, the aircrafts usually follow the zigzag path so that they are always in touch with the DMEs or the VORs, which is the technology on which we have to depend in case we are not having the SBUS system. So this SBUS based systems increase the safety of the aircraft and the passengers. It increases the capacity also, because we will have shorter routes, and that means shorter routes means faster landing and takeoff of the aircrafts, and this will ensure the delays are not happening. Flight efficiencies will be increased, and they are environmental friendly also, because less fuel will be consumed. So SBUS system is very critical to these activities, and this is used world over now, and we should increase the use of it in India also, because what happens that particularly for the tabletop airports, where in the hilly regions we have smaller runway lengths, these SBUS enabled systems can ensure the safety of the aircraft and the passengers by providing higher accuracy. So as shown in this slide, what we can see that during the movement, the horizontal accuracy is coming up to 36 meters for the GPS and 77 meters for the vertical accuracy. And these can be further improved to 2.9 meter and 4.3 meter for horizontal and vertical accuracies. However, if it is SBUS enabled, we can see that the accuracies can go high up to 70 centimeter in horizontal and 1.2 meter in vertical. So that this enables optimized use of the runway and increase the safety of the aircraft. So this kind of system should be utilized by the aircrafts now in particular. The signals of the Gagan, that is for the Indian SBUS. So when we procure our SBUS enabled GPS, then we should ask that SBUS means for us it is Gagan. If they say it is VAS enabled, that means VAS will be there. But VAS is to be used in the US. For Indian region, it is the Gagan. Another thing I've just forgot. Yeah, in this diagram, see when aircrafts are moving from one region to the another region, these SBUS enabled receivers can switch on the service also. So like if they are moving from the Gagan to the Indian to the Chinese and Russian region, they can switch to STCM for Japanese region, to the AMSAS for European region, to the IGNOS. So that switching is also possible. For US, it is VAS. So that switching can be done for the aircraft positioning during the travel. So these signals are certified for the en route operations from 2013 onward. And for precision approach services, it is enabled from the and certified from 2015. Gagan is the first SBUS system which is made available to serve in the equatorial region. So SBUS services are very highly accurate. So we will get 1 to 3 meter of accuracy with it. So for the pilot, it is very much comfortable to take decisions for the landing and takeoff operations using the Gagan. So these are the ground stations for the Gagan from Trivandrum, Bangalore to Jammu, Delhi, Gaya, Dibrugarh and Porbandar and Jaisalmer in the west. So like that, we have a network of Gagan ground stations. And as we can see here, through the high frequency antennas, VHF antennas, we can send the signals to the geostationary orbit and they can be sent back to the users, or the signals can be directly sent to the aircraft also. So both the things are there. And the nearer the aircraft will be to the airport, because what happens, the accuracy will be high near the ground station locations. As we go away from the ground station location, the accuracy will decrease. So for during the landing and takeoff operations, we should, although it will be automated in the system, software will take care, but the nearest airport values will be utilized because the troposphere, ionosphere and all corrections have been applied in accordance to that. So here it is shown again that the Indian reference stations are there and the GPS satellites signals are being received by the reference stations. The correction parameters are generated here using the errors which is found with the known values and the broadcast ephemeris data. And through the uplink station, these are uplinked to the GSAT 8, 10 and 15, which further send back the signals to the user. So all the advantages which we have with any other SBUS, same advantages we have with the Gagan also for optimized path, increased safety of the user, increased capacity for the airspace. And when we are flying with the Gagan also, then because of the higher accuracy in position, we can increase the density of the aircrafts also, because the traffic has increased in the past. Currently, of course, it is relatively down because of the less movement of people due to pandemic. But otherwise, we have seen recently, up to 2 years back, that we have highly congested airspaces, and many times the aircrafts take a lot of time to land, and they are moving in and around the airport because of the other aircrafts which are in the queue to land actually. So these kind of things can be highly optimized by use of the Gagan. Now this is a study by Space Application Center, Ahmedabad, that this total electron content TEC network is there all over the Indian region, which has been utilized for the correction of the ionospheric parameters. So the ionospheric grid points are shown in this figure. So what happens, instead of going for global models, it is better to use our regional models and the regional services which has been developed by the government agencies like the Gagan service, because they provide better solutions, because we have our own observations in our region which enable us to have better corrections, because in the regional models a lot of approximations are there, the regional and the global solutions. So why not to have our own solutions which we have generated, because in our area we have our own observations on the ground. So real-time observations are there which can be used for validation of models and do improvisations in the model. So our suggestion is that the aircraft industry should use the Gagan services. So that was about the IRNSS and the SPAS. Then we will come to the continuously operating reference stations. So there are about 200 private, public and academic organizations working all over the globe with a network of more than 2000 GPS tracking stations which work 365 days, 24 hours. And they provide a very good database for any kind of disaster which take place, particularly because of tsunami and earthquake. Because since they continuously operate, the amount of movement can be computed from these course stations very accurately. So in India, the course stations are maintained by the Department of Space, Department of Science and Technology, Survey of India and Ministry of Earth Sciences, National Institute of Seismology. So large number of course network has been put up in India. Now the SOI is going with a very big plan, and already they have completed it in 2-3 states. So SOI is putting around 900 plus course stations in Indian region. And this course station data will be available to the users based on the request. The form is available on the SOI website. So you can fill that and get access to it. So in that case, from a general user perspective, this course data can be used for the app development, for DGPS solutions also, because these stations can be utilized as the base stations if they are in your study area, particularly or near your study area, and you can just do the survey with the help of the rover station. So basically your liability reduces if you are able to use the course data. So manpower requirement and a lot of things they reduce by 1/2 because we need not to look at the base station establishment. So course network will be very useful in the days to come. Already 2-3 states they are able to use it for various governmental projects and research work. Then the global differential GPS, GDGPS, is another mission or project by the JPL, where it provides real-time positioning, timing, and determination requirements for the NASA science missions. So they have a network all across the globe, as you can see, and without additional infrastructure, with the existing structure, the US agencies are capable of getting accuracy better than 10 centimeter anywhere, anytime, globally. Okay, so this GD-GPS system is there with them, and they are in developmental stage for the tracking and data relay satellite system based positioning also. That is called the task service, because large number of small satellites are also being launched now. So for this from satellite to satellite communication and further communications with the ground, they are developing a technology where the near Earth spacecrafts can be located within an accuracy of 4 inches or about 10 centimeter. Okay, so currently mostly what we are knowing about the satellite position is of the order of 1 to 3 meter. But with this task service in place, which is based on the IRNSS system, the objective is to get an accuracy of the order of better than 10 centimeter. Now, besides this, the international GNSS service is also maintaining a host of stations for global studies with common mandates and participating countries. So about 80 plus countries are participating in it, and 506 monitoring stations are working globally for the IGS, and these IGS station datasets are highly utilizable. And when we survey for high accurate networks, what we can do it, our base station first we can process with the IGS station data, and later we can use the corrected value for the base station as the base station value for our DGPS processing. So these are various type of or different models of the GPS antennas as shown in the slide. This cap type of structure, what you see here, that is the radome. Although the most of the GPS, they are quite rugged and they are water resistant also, but these radome also safe it if you are establishing in a high rainfall area or in the snowfall regions. So this radome is also utilizable there. So if we want to have a GIS analysis with the GPS, then the GPS datasets can be seen as a point, line, or a area. So a set of points will make area line, and a set of them will make a area also by closing the polygon. Now, depending upon the type of accuracy required, we can use the geodetic grid receivers for high accuracy or navigation grid receivers for navigation purpose. Survey grid receivers for the surveying also, where we, as per the type of the accuracy we are aiming at. So now currently we have a lot of handheld models like Mayo from Trimble. This is from Compaq. So these handheld devices, they are quite versatile. They have a GPS antenna in it. They have a SIM slot for the mobile services or mobile SIM-based data transfer also that is possible. Camera is there. Then GIS software can also be installed in it. Inertial sensors are also available, and then the modems are also there. So for real-time activity also, these can be utilized. So Zuno model is there from Trimble, Zeno model is there from the Leica, Yuma pad is there. And then there is a device called Smart Station from Leica, which is an integration of total station and the GPS or the GNSS. So with the help of this smart station, it is possible to take the mean sea level observations and the WGS84 datum-based observations together. So then and there itself, it is possible to compute the geoid undulation also. So a smart station can be really helpful for engineers which are working in the field and using the topo sheets which are based on the old system with the Everest ellipsoid and the mean sea level observations and the other equipments which they use and which are operating on the GPS. So for field engineers, this kind of smart station is highly utilizable. Now, as I have told you, now the smartphones are there which has Android in it, and the IRNSS related packages are also embedded in it. Somebody has asked yesterday a question on the programming and part. So in the API level 29, we have the IRNSS related packages. These you can utilize for the taking of the apps using the IRNSS signals. The other signals, Vido, Galileo, GLONASS, and GPS, they are available in the API level 24. So these can be very well utilized by the app developers for any application. For us, like we are using the aerial datasets, UAV datasets, satellite images, and underwater images also. So there we are using the GPS data for the purpose of the triangulation of the stereo datasets, or if the mono datasets are there, for the georeferencing of them. Because very high spatial resolution datasets are available now, 2 to 5 centimeter datasets are available from UAV data, which has spatial resolution. Some latest UAVs, they are able to provide a spatial resolution of the order of 5 millimeter also. So in such cases, GPS plays a very important role by providing a very good control point. What is the control point? That also was asked yesterday. So control point means basically a point whose coordinates are known. Okay, so such points are not available just like that. So either we can pick them from the topo sheets or from the GPS survey. Now, from the topo sheets, if we pick up the point, the accuracies will be quite low, and they may not meet the requirements of the UAV dataset or the aerial dataset. So that's why we do the GPS survey. So the ground control survey we plan for the photogrammetric activities, and during the interior orientation, relative orientation, and the absolute orientation, we use the GCPs for the scaling and leveling at the absolute orientation stage in the triangulation. Okay, for those who have some background with the photogrammetry. Okay, so this is also one of the applications actually, and these are very usable in the mapping process. So this is the schematic diagram for the analytical or analog stereo plotters, where we have diapositives in use, and we can generate the 3D view, which we can see through the eyepiece, and corresponding maps can be prepared. These are different kind of photogrammetric systems, analytical, analog. This is an analog system. These are analytical ones, this one and this one, and this also, whereas this is the digital system. And this shows the camera, RMKA, 15 centimeter focal length and 23-inch format. That is 23 centimeter by 23 centimeter. It is called 9-inch format basically. This is one of the aerial photographs over which the GCPs are marked. This used to come as a sample with the analog systems. This shows the part of the Europe, Switzerland actually. So similar surveys we have carried out in the Jammu Kashmir for the Katra Kazigund Railway. This is the planned network. So we have done the corridor survey by aerial flight, and then the followed GPS survey and the mapping activity, and then we have generated the contours of this region and provided to the IRCON. Then this is showing another study where see, in case it is not possible to go into the difficult areas and we need height, so the space-bound LiDAR sensors like the ISET1 and the ISET2, they can also provide a good estimate to the height at a particular point. Only problem is that in this kind of data set, it is discrete data. So we cannot have continuous observations. However, we can make profiles of the terrain along the path of the satellite. So this satellite works at a frequency of 10,000 hertz and with a footprint of about 13 meters. And it is a using the photon count based system. So it is a very highly accurate system actually for many applications. So this can be a quite good alternative for estimation of heights in the inaccessible regions. It is a very quite dense data set actually, I said too. So people should look forward to use it also. This shows an application where we have from Dehradun to Kalam and Chandigarh and starting of the Punjab region. Chandigarh is there. So this we have surveyed using the DGPS survey. This shows the base station and this shows the ground control point. This one we have taken as a corner of the bridge. So these we can see in the satellite data set. So this is the DM generated from the Cartosat 1 data. So these are the control points we have utilized for the various basins here. Basically, our planning was with respect to the Cartosat scenes so that we can have a good control over the study area. However, the study was actually divided basin wise for various objectives. Ortho images can also be generated. So this is another study where the geoid height, the orthometric height and the geoid undulation and the GPS heights, they have a relationship, and we have computed the mean and standard deviation between the GPS elevation values and the EGM values using the conversion equation for the assessment of the different EGM models. So definitely as of now, EGM 2008 is giving the best shape of the Earth and the best geoid model, which represent the equipotential gravitational surface. However, most of the open source datasets, they are referring to the EGM 96. So most of the times we use EGM 96 in our computation also. This is another study which shows use of artificial markers when we have study areas where there is lack of contrast and we do not have good control points like the road cross sections or road river cross section or road canal intersection. So those points are not available. So on island, this is for the Maldives actually. So these are white sand islands actually. So what we have done, we have used artificial markers here. And over that, we have put the GPS at the time of the flying. And after that also for the triangulation. So GPS is utilized in such a way also for the photogrammetric applications where map making is the objective. The GPS data can also help us to assess the accuracy of various digital elevation models which are available as open source data on the web-based platforms. So globally we have eTopo for the bathymetry, GTopo for the land-based DEM at a coarser resolution of 1 kilometer. eTopo is available at 1 kilometer and 2 kilometer spatial resolution. SRDM is available in C-band for globally, and for some areas it is available in X-band from DLR website. Then Astra DM is there. So some of the DMs are based on the satellite photogrammetry, some are based on the SAR interferometric technique. So currently LS Pulsar is available at 12.5 meter and 30 meter resolution, LS Prism at 30 meter resolution, and DMX at 90 meter resolution. For the entire Indian region, Cartodem is available at 30 meter spatial resolution. For government projects, we can access the 10 meter data also. However, the 30 meter data is openly available on the Bhuvan platform. Then there are assimilated or merged DMs, which are basically the fused products of SRTM, ESTER, or spaceborne LiDAR. So NASA DM has used most of them. However, Merit and NVSat are using few of them only, like the LOS DM is used and the SRTM DEM is used by Merit. So what happened in this merged DMs, the output, new fused DM is the output, which has higher accuracy than the input DMs. For the assessment of these DMs also, GPS data is very much useful. Even ISET data can also be, spaceborne lidar data set can also be utilized for the assessment of these DMs. This is the NASA DM website from where we can download the chips for the DM for any of the sites. For the processing, we are mostly using the Leica Geo Office or the Trimble Business Center from the Trimble for our processing at IRS. Otherwise, there is a host of other softwares also which are available from Spectra Precision, GPS Survey, GPSS, GraphNav, and all other vendors also. These are commercial softwares which are coming with the faster processing. However, some meteorological data inputs are not having much flexibilities in these. But for scientific community, there are other softwares like the Bernice from University of Bern. So here we can have input for the meteorological data also for better corrections for the ionosphere, troposphere also. Open source is there, Gamut is available as open source, Article Lab is there, GLab is also there. So they are available for free download and use by the users. So out of these, Gamut and Bernice are quite commonly used for the scientific applications. So that is what we wanted to discuss today in continuation to the yesterday's lecture. So I will just brief what we have done yesterday and today. So we have seen that we are getting an accuracy of the order of 10 to 20 meter in general from any of these devices, either alone or combined used. When we want better accuracy, then we are going for the SBAS solution, satellite-based augmentation solutions, where we are using the ground stations which have known location, because there from the broadcast FMRS data we can compute the errors which can be utilized for the generation of the correction parameters. Okay, and then we have seen that Indian Regional Navigation Satellite System that is also fully operational since 2016, and IRNSS is a total independent system. So particularly for the Indian course participants and the Indian region, we should move ahead and we should use the IRNSS and the Gagan to the maximum use. Okay. Then we have seen the survey can also be done either in the static mode, rapid static mode, stop and go method, and the kinematic GPS method. So these methods can also be used for achieving the desired accuracies of the applications. So I will stop here now.